Now, we are going to move into what I consider a little bit more logical progression of chemistry. Our first two units that we really covered were fine, given a stronger chemistry background. But in all honesty, I like to begin my chemistry discussions with the atom. I'm very much an atoms first kind of approach to this. And in this portion of chapter 4 of the elusive little electron, we're going to focus on theory and structure. I'm going to split this chapter up a little bit, and we're going to take a look at periodicity, which is more of a function issue, periodic trends, in a little bit separate section that we'll have a significant inquiry over rather than a large test. So we're going to look at periodic trends separately. And this time we're going to be looking at the theory and then models for our understanding of the structure of the atom. So we need to start with some dead guys. Now, I like to call this my wheel o' dead guys. Wheel o' dead guys. Let's get a better color for you there. Now, that doesn't mean these dead guys are not important, and there's actually a dead gal in here, but I'm a Yankee, and you know the phrase, hopefully, that you might be a Yankee if you say you guys, even if it's a bunch of girls. So you've probably heard me say it way too often. But we're not going to spend any time really on Marie Curie, not that she's not important, it's just not paramount or primary to our discussion right now. So it starts in the early 1800s, really long time ago. This is such a cursory look at this. But I think that we'll hit on some of the important contributions. And one of our goals as we go through these, a few of these, we're going to skip this and we'll mention Planck and actually use his little constant all the time. We'll look at Millikan and Rutherford. Especially then going to focus into Niels Bohr, mention Heisenberg, and then look at the Schrödinger equation. And that gets us into what we call the quantum mechanical model by then. And really that quantum mechanical model certainly started sooner than that. And there's so many missing important people that we just don't have time to look at. Because my key focus on this is looking at the evolution of a model. We're dealing with atoms that we can't really see, although scientists are very, very close to seeing a lot. There's a really cool technique called, I think it was called atomic force microscopy, where they could look at a surface and really envision each individual atom on a surface. They used that in the semiconductor industry. It was very cool. I'll see if I can find some pictures of that for you in class. So let's get started with this. And when we look at our models, there's a few types that we're going to be looking at. We're going to be looking at mathematical models. We'll look at picture models and word models. There's a lot of ways. I mean, basically chemical symbols are word models. And what our goal is to find a way to communicate in our big macroscopic world that we can wrap our eyes around and communicate what's happening at the microscopic level, the atomic level, that is much harder to envision. Now, we're going to jump right in with J.J. Thomson. Talked about Dalton and pre-AP. I want to look at J.J. Thomson's experiment with a cathode ray tube. So, oops, man, oh man, that is a typo. His name is not spelt with a P. That has been around for a while, and I keep missing that. I apologize. Now, J.J. Thomson did an experiment with a cathode ray tube, and they're very fun to play with. I bet they have one in physics. You may get to see one if you take AP Physics. And in this cathode ray tube, we have the cathode down here, an electrical source, and we're going to form a ray of particles. Now, in this case, what we are looking at is a ray of electrons, and they can be accelerated through plates like that. And at this point, we've got a magnet. And we're going to see in a number of different situations that charged particles respond in the presence of a magnet. And what J.J. Thomson saw is that the electrons were ultimately bent towards a positive. So you can't quite see it here, but there's positive. And we'll look at some of the other issues later. It's mainly the electrons that I want to focus on right now. So he made a discovery that we had a negatively charged particle that we now call the electron. And he was able to determine the mass to charge ratio of that electron. So not exactly the mass, not exactly the charge, but the mass to charge ratio for that. Now, as we go into the next one, and again, how much you'll be tested on these is somewhat questionable, but I think it's important to know these contributions, and the names will pop up in different contexts. Now, back with J.J. Thomson, I forgot to mention, he came up with what's called the plum pudding model. And the plum pudding model came up, he proposed there's some sort of diffuse sphere of positive charge. Really hadn't proposed quite a positive particle yet. And these negative electrons are like hanging in it. So it's almost like this positive force field with negative particles. And the reason he called it plum pudding is that the electrons are the little bits of plum, and that force field, that positive force field, could be imagined as the pudding. And so Rutherford, among others, wanted to test this. So Millikan and Rutherford were able to do some tests and make their contributions to this. Now, I've got separate videos of these, and in your assignments of videos, I'm going to give you the links because they are really, really wonderful links. And I want you to make sure you take a look at those. And those will be required. So for those links, I want you to make sure that in your notes, you take notes so that I know that you watched those two videos. The one on Rutherford especially is probably the best explanation of Rutherford's experiment that I have ever heard. In fact, I didn't really understand it until I was watching this video. Not that I'd really focused on it, but still, I think it's a very, very good video. Now, what's missing here, it just was a transfer from my PowerPoint into my Mimeo, is let's look at Bohr's contribution. So I think it would be a good idea if you watch these as soon as I'm done with Bohr. We'll stop this video, and I want you to watch the other ones right away. Now, Bohr came up with a model, and we're going to spend a lot more time on his in a minute. So I'm just going to introduce his model. This is more of an introduction to the dead guys. He proposed that the electrons somehow, that's why I call my book The Elusive Little Electron, because we really don't know how exactly, move around the nucleus. But this is his key contribution. And the concept of energy levels. Now, there are aspects of the Bohr model that irritates me, but it's really not Bohr as much as it is too many elementary and middle school teachers that have students make models of the atom in which electrons are orbiting the nucleus like planets orbit the sun. And that is simply not the case in the situation with the electrons. We're not sure where they are. We're going to talk about a region in space where there's a 90% probability of finding an electron with a given energy. Say that a few times fast. And I like to call that the electron playground. I know some people get kind of aggravated if you use too many analogies and words like that. It's not like electrons play, but I think it's a good image of what we have for our electrons. It's this region in space. They each have their little playground that they're going to be found in most of the time. Now, he found that the electron playgrounds occur in energy levels, and this is key. Not all energy levels are allowed. And when we talk about allowed, that's kind of a funny word because it's not like there's a parent, the little proton parent and the little neutron parent, telling the electron what to do. But when we talk about allowed, the terms I like to use is physically meaningful, maybe reasonable, mathematically feasible, physically meaningful, I meant to put meaningful, mathematically feasible. It's just not, it doesn't come out of the mathematics that we understand. So that's what we mean by allowed. We're just not going to see it. And it really all gets down to, and we'll ultimately be focusing on this, why isn't it mathematically feasible? Why isn't it physically reasonable or meaningful? It's going to be about electron repulsion, and then the attraction of electrons to that positive nucleus. And that's really what dictates it when we get down to the structure function level. And so what we call that is we say that the energy levels are said to be quantized. You need to fill in your blank there. Quantized. So an analogy to this would be that a continuum is like a ramp in which, in theory, every single height as you go up that ramp is allowed. If you just scoot as tiny steps as possible. Whereas quantized is more like a staircase. All right, you can go up one stair, you can go up 2 stairs if you have really long legs. I had a student who could almost effectively step up on top of our lab benches, and he wasn't that tall. It just was fun to watch. You can go up more than 1 step, but you're not going to go up half a step and hover. If you overshoot a step, you're just going to land down on top of it. And so only discrete heights above the ground are allowed. And that's really what we're getting at with the concept of quantized. Now, a key difference with quantized is that the steps aren't all the same height, which of course makes humans trip. But all analogies have to end somewhere. Now, in the next series of videos, we're going to look at the 3 key subatomic particles and what happens when there are changes in each of those. So look forward to seeing you back soon.